Okay, welcome everyone. It's my pleasure to introduce Thomas, one of our organizers. He's going to be talking about a family of rational VOAs as type C cosets.
Yeah, thanks, Flora. So hi everybody. You probably all know what Vladimir and Andy and others like me are doing, and sometimes at the moment we are interested in universal structures, kind of large two-parameter families of VOAs that allow to prove interesting things. And the main thing I want to go to today is to give you a quite pretty proof, I think, of a new rationality result. But the main part of my talk will be the motivation. So we kind of believe that basically every VOA can be built out of parts. And if you think about the VOAs that you know, any VOA that I know at least is somehow built out of an affine VOA. You can take tensor products of affine VOAs, that's the VOA again. You can extend it. For example, lattice VOA is nothing but an extension of a Heisenberg VOA. And then you can look at sub-VOAs, invariant sub-VOAs like orbifolds or cosets. And one very important construction is, of course, also the quantum Hamiltonian induction, which gives you the W algebras. And W algebras, in fact, give you a huge zoo of the VOAs, namely because W algebras, they are parameterized, of course, by the Lie algebra, a choice of level, and a choice of nilpotent element. And we would like to get a better feeling what this zoo of W algebra looks like. And so the general setup is, so you start with a VOA, think about it as a W algebra. That VOA has some weighted two space, say some of some given dimension. And in a nice situation, so this doesn't need to hold always, so I have to assume it. But very often the situation is that this weight two space is simply spanned by a bunch of Virasoro vector, a bunch of pairwise commuting Virasoro vectors, so that your total Virasoro element is just the sum of these. And in particular, what this means is your big VOA is an extension of n commuting Virasoro algebras. Now, usually what will happen is that it's not just an extension of these Virasoro algebras, but each of those extends to a larger VOA itself. So here I call this W1 up to Wn. And that is some kind of quite a generic situation. So you can scan your examples of VOAs, and usually you can, I would imagine, do this decomposition into Virasoro vectors. Of course, not always, and unfortunately, for example, for W algebras, that is something not known and hard to show. So anyway, in such a situation, we could say that these n sub-VOAs, W1, W2, up to Wn, are building blocks that build out our big VOA. And if we are in the situation that we understand our building blocks well enough, then, well, we might understand quite a bit also about our extension in general. So, and the belief that we have is that there aren't so many possible building blocks. There are simply, for each type of VOA, there's also a type of universal structure that serves as a building block. And so really the overall goal one should view as, and if you fix your rough type of VOA, and then you are looking for universal structures that serve as building blocks, and use that to kind of get some structure on your family of VOAs. And this whole idea is mostly inspired by the universal structure or structures that we do know well. So the one that we know best is called this W infinity algebra, or W infinity of C and lambda. So I imagine many of you have heard of it. This is a two-parameter family of VOAs, so which are these parameters C and lambda, which you should think about, meaning it is a VOA, not over the complex numbers, but over rational functions in these parameters. So each OPE coefficient is a rational function in these two parameters. And this VOA is in fact huge. Namely, it is not finitely strongly generated. It has one strong generator in each conformal weight starting at 2. So it's often also called W infinity because it has infinitely many strong generators, and it's often also called the W infinity algebra of type 2, 3, 4, 5 up to infinity. Okay. Now, and now, okay, so this is a VOA whose coefficients are rational functions in the parameters, and in particular, I can specialize. And if I specialize to generic parameters, you'll just get a simple VOA, very much as you are used to specialization. Right, if you can, for example, an affine VOA is a vertex algebra over polynomials, in fact, in one parameter, a level. And you can specialize this, and as long as you specialize it to an irrational number or a rational number that is not too positive, then you get, in fact, a simple VOA. And here in this two-parameter family, the situation is similar, but more interesting, of course. It's two parameters. So in particular, there are many, many interesting one-parameter subfamilies. So and for which this W infinity is not simple, and so it allows for nice truncations, meaning nice simple quotient. And so, for example, this W infinity has all the principal W algebras of type A as such one-parameter quotients. And so you see here already that the word W algebra of type A appears, and indeed this Andy's W infinity algebra is the thing, the universal structure that we want to that we want to think about as the building block for W algebras of type A. So let me explain this a little bit more in more general. So I really don't care whether we now take G to be GLN or SLN. Sometimes GLN is just a bit nicer to handle. It doesn't make a difference really. So for type A, for GLN, it's the different types of W algebras are easy to state. So what you do is you simply you fix a partition of your capital N of the GLN, meaning you fix a tuple of positive integers that add up to n. And of course, you can order them. It's kind of nice to order them. So our convention is here that the first entry n1 is the largest one, and then they get smaller and smaller. In particular, usually one likes to visualize these partitions by Young tableau, meaning you just write the tableau consists of these capital N boxes. The very lowest row is the longest one. It has N1 boxes. On top, you write a row that has N2 boxes, etc. And often, in fact, you call your W algebra after the shape of the Young tableau. So, for example, kind of really nice family are the rectangular W algebras where the shape of the Young tableau is a rectangle. Okay, and now to each such partition, one associates a nilpotent element in G, and you can imagine what this is. So what is the partition of the big N into R integers? What you think about it is you have your big N by N matrix, and now you have on the diagonal, you draw many diagonal blocks of the first one and N1 times N1 block, the second one and N2 times N2 block, etc. And what does this give you? It gives you the obvious, the natural embedding of GLN1 plus GLN2, etc. into your big GLN. And in particular, the corresponding nilpotent element is just the image of the nilpotent element in the subalgebra under this embedding. And then, yeah, you get a W algebra via quantum Hamiltonian reduction. I'm sure most of you know that, and it depends very much on your choice of partition here. And it is a nice one-parameter family of VOA that has some importance in various areas, and mostly, I would say, to the geometry, identity-quiver varieties, etc. They appear, but also many other things. So Shigenori and Justine, who are here, they did something very nice. So if you now fix your favorite Lie algebra and your favorite nilpotent element, the moment your partition is kind of too far away from the trivial partition, meaning 1, 1, 1, 1, 1, and or if your Lie algebra 2 has the rank is too high, then you really in practice have no knowledge what the OPE algebra of this W algebras looks like. So to give you an example, there's closed formulas. So the partition 1, 1, 1, 1, 1 corresponds to the affine VOA. For that, of course, we know very well what the OPEs look like. Then the next simplest partition is 2, and then comma many ones. And this gives rise to the so-called minimal W algebras of type GLN. And for those, Kast and Wakimoto also wrote down a closed formula of fields, and then in particular also of OPEs of generating fields. But beyond that, it's more or less nothing is known. And Justine and Shigenori, they wrote a computer program that computes these OPEs. Of course, it's also then restricted to lower rank, but it's still quite good. And so in particular, we all were led to this following conjecture. In fact, we conjecture something more general, but for the purpose of this talk, I phrase it in this specialized form. So for type A, if our nilpotent element as I explained, and then S is roughly the number of the R, then the number of the number of rows the Young tableau has, or R minus 1. And our conjecture is that the W algebra of type A, of type GLN, that we obtain in this way, is built out of S, so of a bunch of W infinity quotients of Andy's type, together with a bunch of Heisenberg VOAs. In fact, one could have incorporated this Heisenberg VOAs by immediately defining W infinity as W1 plus infinity, including a Heisenberg field, which in fact physicists often do. And so this conjecture has a longer motivation. It is in fact so I came about it from geometric considerations, and so for example, one believes that W algebras of type A are related to twisted shifted affine Youngins, and they have some structure called Gelfand-Sedlin basis or something like this, and the translation to these affine Youngins are supposed to correspond to universal structures that contain W algebras of corresponding Young tableau shape. So the Young tableau shape is related to the shift of the Youngin, twist shift of the Youngin. And this Gelfand-Sedlin basis correspond to the factors of W infinities. Anyway, so this conjecture, one shouldn't say is our idea. We write it down. Surely somebody else was aware of it. It's not really stated in the literature anyway. And we'll have an article which maybe will appear in a few weeks, I don't know. It's this conjecture, in fact, is true for the cases that we can check. So, which you should take really as a quite non-trivial result. It's not, yeah. Anyway, I'm still in the motivation part here. So now you can ask, good, this is a conjecture. Well, you can conjecture a lot. If you find it interesting, you can prove it. Now, then you can ask what is good for. And okay, if you care about these relations to geometry, you have your point, and that's maybe actually the reason why you should care about it. But one thing also VOA theory is somehow desperate for to find VOAs that have a very nice representation category, right? And so we call those VOAs Lis or Lis and rational if we want also semi-simplicity, or Lis of so C2 cofinite, right? Because Lis VOAs are those that have only finitely many simple modules, and that's of course really really nice. And if one scans the zoo of such VOAs that one knows, then first of all, almost all Lis VOAs, all C2 cofinite VOAs that we do know are also rational, that means semi-simple. And moreover, the rationals that we do know are, of course, the positive integer level affine VOAs, the Westermann-Witten theories, and its quantum Hamiltonian reductions with respect to a nilpotent element that is compatible with a level. So this is Tomiyuki's famous story, right? It depends if your level is admissible, that means positive rational enough. Then Tomiyuki has proven that as long as that the denominator of the level shifted levels of a certain type corresponding to the nilpotent element, you get a C2 cofinite VOA, and then rationality was also eventually done with the help of Jethro Robert. So, and I mean, you know, there were people who proved one case after the other. Justine also proved a few cases. Annie and I did. Many people did. Now, and in particular, you should. So for our perspective, is we have this really interesting two-parameter structure, this W infinity of Andy. It has this really nice one-parameter subquotients that have nice interpretation in terms of W algebras. They are conjecturally the building blocks of all W algebras of type A. And now you can, of course, specialize further, right? So now you can take your level to be a good rational number, for example. Then you would very much or your parameters. Then you would hope that maybe sometimes that the simple quotient, I mean, you will quotient by quite a bit, so that the simple quotient has a chance to be Lis and rational or just Lis. And the answer is for the W infinity of Andy, surprisingly rare, maybe. I mean, we didn't prove exhaustiveness, but it's quite likely exhaustive that the only W infinity quotients that are rational in Lis are the principal W algebras of type A. So for the principal nilpotent element, whose rationality Tomiyuki proved a long time ago. Now, if you go back to the conjecture, we would then of course also expect the following. Okay, so now we have our simple W algebra. So I denote here this always with a lower level with a lower index. And now you wonder when is this one C2 cofinite and rational? Well, according to the conjecture, it's an extension of many W infinity quotients. So you would expect that it is rational if all these W infinity quotients are in fact rational in Lis, because then it's an extension of a rational and Lis VOA. And probably you would in fact expect that it's an if and only if statement, but that's a much harder to prove claim. Now, I've been quite bothered with the rationality of VOA extensions, but you would always think that that should be an automatic textbook theorem 20 years ago, right? I mean, the theorem I write down here, right? Let W be a conformal extension of a VOA V, maybe with some niceness properties. So here I only require they are both simple. If you drop simplicity, you can very, very easily construct a counterexample for this theorem. And then you also require this haploid condition that the multiplicity of your sub-VOA V in W is 1. Then this theorem says that a rationality on Lis of V implies the same statement for W, where the C2 cofiniteness is well known and not a big deal. The rationality, the semi-simplicity here is the big thing. And now let me also tell you why this has been bothering me. So this is this note I write down here. So I think many of you have heard about this. I mean, first of all, a vertex algebra that is rational and Lis has in particular the property that its category of modules is a nice semi-simple modular tensor category. And then VOA extensions, that is this nice insight of Wang, Lipowski, and Kirillov, is a one-to-one correspondence to commutative algebras in the category. And so in particular, this extension problem can be completely phrased in terms of a categorical problem, because this is then what Shashank or what and I did that this extension problem also is compatible with the vertex tensor category structure. But interestingly, if you think about this extension problem, it's always there one has the statement is that this extension has also a semi-simple category, provided that this extended algebra has non-zero categorical dimension. Unfortunately, that's very hard to check. And now Harshit Yadav, he's here now in Edmonton, and he has shown me a 3-year-old article by Ettinghoff and Ostrich, who found a really nice new criterion for exactness of module categories. So exactness of module categories means that if you tensor an object in your module category with a projective object in your base category, then you always get a projective object in the module category. So some statement. And it turns out that's now an insight of Shimizu and Harshit, is that this exactness implies rigidity. And with rigidity, it's very easy to prove the theorem. And this is a totally new insight. So Harshit and Shimizu haven't even written their article yet. Anyway, this finishes the first part of my motivation. And now, so the motivation here is, roughly speaking, W algebras of type A. So type A, always the simplest type, can be conjecturally at least built out of a universal structure. And that gives you a kind of, for example, a very good explanation what are the rational W algebras of type A, because they, provided the conjecture is true, they must be precisely the extensions of, they should precisely be the extensions of the of those cases where all building blocks themselves are rational. And which of course should be very rare, explaining that rational W algebras beyond the principal type are not very frequent, which we indeed know they are not. Now you can ask the same question of other for other types, and what comes after A? There comes B, C, D, right? And there again, one has a nice universal structure. It has been constructed by Shashank and Andy. And very much what I said above for type A also holds for this orthosymplectic type, right? So this algebra is just, and it's called even spin W infinity, because in that case, its generators are only of even conformal weight. Yeah, it basically shares all analogous properties as the W infinity, but no for type BCD. But with one crucial difference, if you look at the W algebras of type BCD, you very quickly observe that with the even spin, they can't they can't be all the building blocks. They will be for a nice class of important elements, they will be fine. But there are missing building blocks, and these missing building block, they exactly look like what Vladimir has constructed. And Vladimir has also given a talk in here, and probably some of you know. So he has constructed a third universal structure. In that case, it is it has at each odd conformal weight a triplet of fields, which you should think about as an adjoint of SL2, or better as an adjoint of SP2. And then at each odd even conformal weight, it has a singlet. And the conjecture would be that first of all, the same type of conjecture as for type A holds, in the sense that every W algebra of orthosymplectic type can be built out of a bunch of copies of the even one parameter subquotients of even spin W infinity together with a bunch of copies of one parameter subquotients of the algebra that Vladimir has constructed. And in particular, if one goes on with the motivation, of course, one should study this conjecture, or maybe in fact first put it into words. And my understanding is that Shigenori, Justine, and Vladimir are exactly starting to do that. So you can ask them about that. But then if you go on with this motivation, you would of course also ask, what is it good for? And well, I said, one thing it is good for is that you can now look at when are your building blocks rational to see when are your extended building blocks, your extensions rational. And for the even spin, the rationality is definitely more interesting than in the type A case. So one has the principal W algebras of type B, C, D, where B and C, they are Fagan-Frankel dual, so I don't have to write C here. And they are known to be rational, and here sometimes there's a Z2 orbifold subtlety. But also principal W algebras of OSP1/2n are supposed to be rational. And this is something we've been thinking about quite some time. And at the moment, we have the C2 cofiniteness statement. That's already very good, I would say. And hopefully we can also extend that into rationality. Anyway, the point is even spin already has a bunch of rational results. And now talk today is almost only motivation. Anyway, is the question, what about rational points of Vladimir's algebra? Okay, and now probably one always has to choose a good perspective to achieve what one wants to achieve. And for the principal W algebras of type A, B, C, D, also E, also OSP1/2n, all of them have some kind of nice coset realization. And these coset realizations are always an affine VOA, maybe times a free field algebra, and then a diagonal coset. And this diagonal coset is then as a one parameter VOA, this type of W algebras. So the type ADE are the famous GKO cosets, and yeah, the other ones follow, for example, from Andy and my triality. And here I claim that the rational points, or at least many of rationalist points of Vladimir's algebra, are described by the coset I wrote down here. Namely, a diagonal coset. So you take your affine D algebra, in this case is of type C, SP2n. Now you add 4n free fermions, because 4n free fermions, they carry an action of SP2n at level 1. So that means you have a diagonal action at level k minus 1 plus 1 at level k. And the invariant subalgebra, the coset, is something interesting. In particular, it is in fact a one parameter truncation subquotient of the algebra that Vladimir has constructed. So I always call it of Vladimir type, and Vladimir told me he doesn't like to be so prominently. One could also call it a rectangular W algebra of type C1. That would be, but it's, yeah. anyway, there will be a good name over time. So we have the following statement that this coset is rational endless is rational endless if this level k-1 in the numerator is an admissible level for sp2n. Okay, and now I can start with my proof. So this was the motivation. And I hope you will find it pretty. So the proof has one key observation, and so this is so first of all, let me introduce one number. So this n+1 is the dual Coxeter number of sp2n, and okay, so some number depending on k and n. Now now I claim the following: if k is a positive integer, then there's a conformal embedding. Maybe I will stop writing conformal embeddings. Just not to write so much of the following. The simple affine VOA of OSP1/2n, so of the Lie superalgebra OSP1/2n times the W algebra. And this is why I introduced this L at level L of sp2n inside the big VOA that we ask whose coset we want to study. And this this claim, if you think about it, you will be very surprised about it, right? Because I mean, you can even think about it in terms of strong generators, right? Your big VOA is affine sp2n, so it has the strong generator is given by a basis of sp2n together with this 4n free fermions. And OSP1/2n itself is generated, of course, by a basis of sp2n, together with the odd fields being in the standard representation of sp2n, so 2n odd fields. And it's kind of, I mean, how could this possibly be? So one point is you don't use the standard conformal vector. So here this is not the standard conformal vector. But you give a sum of these fermions conformal weight 1 and 0. So you should maybe more call it a mix of free fermions and BC systems. And but yeah, anyway, so why is this true? And this is really why this whole thing is this is maybe the most interesting thing of the proof. So what you do is you look at the following free field VOA. So and now you take 4n times k, which you should think about as 2n times 2k free fermions times n beta gamma systems. And what you should think about it is as the free field algebra associated to the standard representation of sp2n, so that is c2n, 2n free fermions, times the the standard representation of OSP1. No, for this. You should view it as the free field algebra associated to the standard representation of OSP1/n times the one associated to the standard representation of sp2k. And very often when you have this, then this gives rise to some kind of level rank duality. And in this case, this this also happens. In this case, what's happening here? In this case, the level rank duality is the one that you have an embedding here of your OSP 1/n affine VOA, so exactly the one we are looking for. And its commutant is an affine VOA of type sp2k, and the levels and ranks are somehow interchanged. which is better visible if you take the shifted levels, right? Because in both cases, the level shifted by the dual Coxeter a number are k plus n plus 1/2. So they have the same shifted levels, which is a standard feature of the level rank duality. Okay, so how does this claim now follow? Well, you can now do the minimal quantum Hamiltonian reduction on both sides. The minimal quantum Hamiltonian reduction on the SP I confused here k and an n. This must be here k. So okay, the minimal quantum Hamiltonian reduction of k beta gamma systems is in fact trivial. So this means here on the here on this side you just are left with your many free fermions. But on the right-hand side, it just replaces here. What does it do is it replaces here the affine VOA by its minimal W algebra. And one thing that that follows from the triality of the orthosymplectic triality of Andy and me is that this is a conformal extension of an affine VOA of SP1 rank less times principal W algebra of type SP2N, and the level is exactly the level that I stated above. But now think about what you can you do here about 4n times k free fermions. I can write it as 4n times k minus 1 free fermions times 4n free fermions. And why do I do this? Because in 4n times k minus 1 free fermions, you have also an embedding of the affine VOA of SP2k minus 2, and its commutant is an affine SP2n of level k minus 1. Now, there are quite a few things I now glossed a little bit over. So here I did the quantum Hamiltonian reduction on the these k beta gammas. They carry an action of SP2k at level minus 1/2. And here I did the quantum Hamiltonian reduction on a completely different SP2k, but that these two quantum Hamiltonian reductions are the same is quite a deep theorem called the Urot theorem, which would be a whole talk on its own. And if one follows that the Urot theorem carefully, the proof through, one sees that this affine SP2k minus 2 and these ones are the same. So in particular, that commutants are the same. And so in particular, but here on the left-hand side, the commutant is precisely an SP2n at level k minus 1 times the 4n free fermions. And on the right-hand side, it is exactly the W algebra of S type SP2n times the OSP1 to n. So it's a very interesting, in fact, very deep proof, but I mean, deep mainly because it follows from this Urot theorem. And it's the explanation why there is the OSP1 to n. And if I gave you now the homework problem to compute explicitly what this OSP1 to n looks like, say for n equals 2, for OSP1 4, we'll probably have an extremely hard time to even find it. It's very tricky to compute this. Okay. Anyway, so but now you can think about it. So let me write this down as a corollary. The statement above holds as one parameter VOAs. So let's see what I mean by this and why this is true. By the statement, I mean the claim I write here down, that we have this conformal embedding of the W algebra of SP to N and of the affine VOA of OSP1 to N inside affine VOA of SP to N times 4 and 3 fermions. And we found that this claim is true for every positive integer. So that means for infinitely many levels. And moreover, if you take the level large, then also any singular vectors have very large conformal weight. So in particular, there is this whole claim must already hold for every level, or at least for generic level, in particular as one parameter VOAs. So this means in particular one arrives at this very nice statement that this 4n free fermions times affine VOA of SP to N always carries some kind of diagonal action of OSP1 to N at level K, a result that you should take as very, very surprising. Okay, now now the rest is quite simple of the proof.
Thomas,
So
I think there's a question. Shashank?
yeah,
Oh, sorry, I think I missed something. So where did the universal VOA come into play?
okay, yeah, I'm so it comes. And so now think about this. We have the following problem. We have a general coset problem. So in here it is the diagonal coset of I mean here a one parameter family of VOAs. So here it's the one parameter family is affine VOA of SP to N at level K minus 1. So K is the parameter times these 4n free fermions. And now we have shown that for infinitely many points, namely for each positive integer k, this is a conformal extension of an OSP1 to N at level K and a W algebra at a level L. And then the statement already must hold as one parameter VOAs, just because the structure constants are rational functions in these parameters, and you have countably structure constants, and you have countably many points where you can check it. So it must always hold.
It's the usual. Okay, yeah, sorry.
Yeah. This is the nice thing. This is nothing deep. This is why I just wrote corollary, but of course, it's powerful, but it's a immediate consequence.
I have another question, Thomas. I'm not sure I understood correctly, but did you say it's hopeless to try to realize the embedding explicitly?
Oh, I'm not sure. Yeah, if you're good with computing, sure, you can probably do this.
I see.
I mean,
it's not advisable, maybe. I got you.
So I would be surprised if you had discovered the statement in a different way than I did. And
I understand.
I mean, quite often you discover statements simply by computations or by kind of an obvious logic, and then right, at least for small rank, and then you generalize. Here it is. Here I want to see the person who would have guessed this.
Gotcha. It's not a separate.
Which of course you can give me a reason, but I don't see a natural reason to guess it, which is yeah. I think so. I think I found this statement because I noticed that I noticed the proof.
Mm-hmm.
And then I simply followed this argument through, and at the end we got this OSP1. Plus, I knew that this statement is true for n equals 1, because for n equals 1 it is fairly easy.
I see. Thanks.
Okay. So, where am I? Right now, we restrict to admissible levels, and then so with an L and a lower index, I always denote the simple affine VOA, and it's a well-known statement. If I tensor an admissible affine VOA is simple with an integrable one, then the diagonal action is also given by the simple affine VOA. So this is a 1990 paper by Creutzig, maybe even earlier. And but then it follows, and this is not very much non-trivial, that in fact also the simple OSP 1 to n embeds in our big VOA. And this was a statement I have been struggling quite a bit with, and then luckily I found a paper, also fairly recent, maybe 3 years old, by Gorelek and Saganova, that imply the statement. So the statement follows immediately by their work, which is really nice. Okay, but now, but at admissible level, so now we are done. This is because at admissible level K, the affine VOA of OSP 1 to n has, of course, the affine SP to n in there. And its commutant is also a principal W algebra of type C. And here this L tilde, I never know, is best described by adding up the inverses of the shifted levels. So level plus dual Coxeter number of SP to n, the inverses add up to 2. And yeah. So and this statement follows either by triality or somehow much nicer by something that Andy, Naoki, and I did. But then now you see we are done, and it's good because we're also out of time, because this means, in particular at these levels, it means that our so let me write it down in formulas. So if you put it together, this means we have a conformal conformal extension of these 3 VOAs. They extend conformally to our big VOA. That's what these statements together say. And in particular, but our coset is the coset of the affine SP to n. So this means in particular, our coset of interest is a conformal extension of these 2 W algebras. Let me just write dots of these 2 W algebras of type SP to n. And now one looks at these levels, so they are non-degenerate, principal or co-principal admissible, depending on what K was of the 2. In particular, Tomiyuki proved that they are rational. So this means this coset is an extension of a rational VOA. And now it also explains why I mentioned this theorem here in my note. Okay. So in particular, you should so let's go to the theorem again. This coset here, which is given here again, you should view it as on the very same footing as the GKO coset that realize principal W algebras of type A, DE, or the affine OSP 1 to n, whose SP to n coset realize principal W algebras of type B. And here, this one is now the first coset in the same vein somehow, but it doesn't realize a principal W algebra anymore, but new somehow rational VOAs, we didn't give them any name, that are exactly of the new Vladimir algebra type, and so they should be the ones that serve as building blocks of rational VOAs of orthosymplectic type. Very nice. Thank you for your patience.
Thank you, Thomas. Yeah, thanks. Any questions for Thomas? Please feel free to unmute yourself and ask. And I have one, so I'll start. This new technology of, let me maybe stop the recording so we can all ask freely without being worried about being